Okay, we're continuing the notes on equilibrium and acid-base focus, like chapter 16. So now we're looking at the water ionization and acid-base strength. So water ionization constant, Kw, okay, and so just equilibrium constant, but for water. So water is a molecular substance, and so far we have observed that water does not conduct electrical current, but in fact, water does conduct a small amount of electrical current. Okay, from this observation, scientists infer that pure water self-ionizes, meaning that the two molecules of water can react to form ions. Okay, but like it's really not very common. So about 2 in every billion molecules will actually form these ions. Okay, and so like most electric current isn't read like by our, like you need really good equipment to actually be able to read this electric current. Okay, and so what happens though, in about every billion molecules, the two water molecules collide, okay, and then form hydronium and hydroxide. Okay, and so yeah, like it's less than 10 to the minus 6%. So it doesn't happen very often. Okay, chemists have determined that the concentration of hydronium ions in pure water at 25 degrees Celsius, okay, is 1.0 times 10 to the negative 7 moles per liter. So the ionization of water produces the same low concentration of hydroxide. Yeah, that word's missing, but that's what it should say. And so if we kind of look at our equilibrium constant for this reaction here, so we have hydroxide or hydronium and hydroxide. Okay, remember water, because it's a liquid, doesn't have a concentration, so we just cancel that out. That's not part of our equation. So we get our equilibrium constant is equal to concentration of hydronium times the concentration of hydroxide. Okay, the Kw, water's ionization constant, is equal to, okay, which is equal to this equilibrium constant, is equal to 1.00 times 10 to the minus 14. Okay, so that's the water ionization constant. That is in your data booklet. Okay, you can look that number up. Okay, and so what that tells us, okay, is really like to get this number, the amount of hydronium, which we talked about up here, is 1.0 times 10 to the minus 7, which is equal to the amount of hydroxide. So you put those two numbers together, you get this number. So since ionization constant for water, Kw, so since these two multiplied together equals our Kw, this number here, this is a constant. That's always 1.00 times 10 to the minus 14. So if we know this one and we know one of our other ones, then we can solve for our other concentration. So if we know the concentration of hydroxide, we can find the concentration of hydronium by going Kw divided by the concentration of hydroxide. Okay, if we know the concentration of hydronium, we go Kw divided by hydronium equals hydroxide. So it's just some more equations that you can kind of add in to solve for our number, like our unknown. Okay, I'm going to do these like I did last time on a separate video, all the examples. So we'll look into those in the next video. Okay, a pH scale. So a lot of this we talked about last year. So again, the pH scale is built on the logarithmic scale. Base 10 logs is really how we do it. So basically, like for these ones, so if the logarithm is 10, the logarithm of 10 is 1, because 10 to the power of 1 equals 10. So we basically are taking whatever number's up here, and that's what becomes our logarithm. So the logarithm of 100 is 2, because 10 to the 2 equals 100. So we take this number up here. Okay, so the pH is the negative base 10 logarithm of the molar concentration of hydronium ions in a solution. Okay, and so we did a bunch of these equations last year. So the pH equals the negative log of the hydronium concentration. Okay, when reporting pH values, only the digits to the right of the decimal point are considered significant. You can calculate hydronium concentration from the pH by using the anti-log, which would be the second function to the log button. And so you go 10 to the minus pH would give you the concentration of hydronium. The pOH refers to the power of hydroxide ion concentration. So you can find the pOH of a solution by going pOH is equal to negative log of the hydroxide concentration. You can calculate the hydroxide concentration by finding the antilog of the pOH, it should say there. So the hydroxide concentration is 10 to the negative pOH. Okay, another thing to remember, handy kind of conversion, the pH plus the pOH equals 14. And then along with those calculations, the one we just talked about, the concentration of hydroxide times the concentration of hydronium is equal to Kw. So you can always use that one if you're given concentrations. Okay, so you can go from one concentration to the other concentration by using your equilibrium constant for water. Oops. Okay, so these are kind of the calculations and the things that you need to know as far as how to use it. So the mathematical logarithm allows us to express a relationship between pHs and pOH according to the rules of logarithm. So log AB is equal to log A plus log B. So the equilibrium law for ionization constant of water, so we have concentration of hydronium times the concentration of hydroxide equals Kw, meaning that the log of hydronium plus the log of hydroxide equals the log of the Kw, which really gives, that's where we get like the minus pH plus the negative pOH equals negative 14. We times them all by negative 1. We get pH plus pOH equals 14. You don't have to know how we calculated that. You just have to know that's one of your, like, that's where we get the number that we worked with last year. Okay, and we'll work more with this year. Okay, and so the formulas that we need to know. So Kw is equal to hydronium concentration times hydroxide concentration, which equals 1.0 times 10 to the negative 14. Okay, pH is negative log of hydronium, pOH negative log of hydroxide concentration. Okay, and then if we're going backwards, it'd be the hydronium would be 10 to the negative pH, hydroxide would be 10 to the negative pOH, and at any time we could go pH plus pOH equals 14. Okay, so how do we measure the pH of a solution? Okay, so there's a couple different ways. Okay, the first, acid-base indicators. So we looked at these last year. You have a whole chart in your data booklet full of indicators, okay, and what colors they change depending on the pH of the solution. Okay, and so acid-base indicators can be used at one time, or if you put a couple together, you can create a universal indicator that changes colors kind of for each pH. Okay, a pH meter is the most precise way to measure pH of a solution. Okay, it uses an ion-specific electrode that compares the concentration of hydronium in the solution with a reference electrode.